Good afternoon.
Hello, nice to see you guys. Okay, so last time we introduced Kirchhoff's laws, in particular his junction law and loop law. So I guess today we will start from defining them again, just to recall, and then we will proceed with some example of applying these rules on some electric circuit. Afterwards, we will start to discuss another topic, which is RC circuits, like resistor capacitor circuits, which involve some time-dependent electric current. So it's still DC current since it doesn't change the direction over time. However, in this case, we will deal with not constant but time-dependent electric current. Okay, then probably let's go into this. So, just to recall these two Kirchhoff's rules. So, first one is so-called junction rule, and actually means that the sum of all electric currents which come and go out from the junction is equal to 0. So this comes from the law of conservation of electric charge. We don't lose charges anywhere, don't generate new, as many charges came to the junction, as many charges should go out from the junction. In this case, this is the direct result of the law of conservation of electric charge. So second law is so-called loop law. Assumes that the sum of all potential drops over resistors, like all resistors in the closed loop of electric circuit, should be equal to the sum of electromotive forces which are located in this closed loop electric circuit. So we will, how it works, we need to define some direction of path for which we will consider current and electromotive force positive, and then depends on our orientation of this electromotive force sources and direction of current through resistors. They will be either positive or negative, and the sum of them should be equal to 0, or the sum of potential drops over resistors should be equal to the sum of electromotive force in this loop. So this will be better to show on some real example, and that will be more clear. So let us consider such equivalent circuit. Some electric circuit with two electromotive force sources. and bunch of resistors. And one will be here. So looking at this electric circuit, we see that we cannot simplify it by applying these rules for connecting series and shunt resistors. In order to deal with such electric circuit, we need to apply Kirchhoff's rules. So let's say we have, this will be our epsilon 1. This is epsilon 2 electromotive forces. We neglect with internal resistance of these batteries. Then we have, let's say, R1, R2, and R3. We have 3 resistors, and now we need to define just arbitrary from common sense, let's say, let's define the directions of currents through each of these resistors. So I would define it like this. We have current through resistor R2, which will be I2. Then we have current through resistor I3. And we have one more current, which will be I1 through resistor R1. So now let's assume that we know all parameters of this electric circuit. So we know electromotive forces and we know resistors. So our task is to find unknown electric currents which flow through each of these resistors. So I1, I2, and I3 are not known. So as I mentioned last lecture, by applying Kirchhoff's laws, we get a system of linear equations, and by solving this, we can get unknown parameters. If we have 3 unknown parameters, according to the rules of laws of linear algebra, we need a system of minimum 3 equations. So now we need to build up a system of 3 equations in order to solve this problem. So let us start with the junction law. Let's mark these points here because we will need them. So it will be A, B, C, and D. So let us consider first the junction C. So we have junction C. So what do we have here? We have current I2 and current I3 flowing in, and current I1 flowing out from this junction. So in this case, we can write that I1 is equal to I2 plus I3. So we have one equation already, which defines the how different current through different resistors depend on each other. So now we need to go and consider, apply the loop law, like second Kirchhoff's law, twice for two closed loops of this electric circuit. And before we are doing this, we need to define which loop we consider. So let us consider first loop, which is A, B, C, and D. So this external loop. And we need to choose the path along which we will consider the components of this electric circuit. And their contribution in terms of change of potential. So let us consider clockwise path along this loop. And in this case, what we see that current, so we have two electromotive forces, and current I3 flows. So we have two types of two currents, I3 and I2, and two electromotive forces. So current I3 flows in the direction of our path, so clockwise. In this case, we can consider that epsilon 1 is positive, and then we see that epsilon 2 is oriented in opposite direction from the path which we have chosen. So this current I2 flows kind of counterclockwise. And that's why we have considered this epsilon 2 for this particular configuration as negative. So it will be epsilon 1 minus epsilon 2. And this will be equal to the sum of potential. So the sum of electromotive forces should be equal to the sum of potential drops over resistors. So here we have similar case. We have for resistor R3, current I3 flows in the direction of our path, like clockwise. So that will be positive, I3 times R3. And then we have another resistors R2. In this case, current flows kind of counterclockwise, opposite to the path which we consider as positive direction. And that's why we subtract this product I2 R2. So now we have this second equation for external loop ABCD according to the loop law or second Kirchhoff's law. We need one more. And for this, let us consider a loop which is defined by points A, D, C. So it will be A, D, C. Here we select the path counterclockwise. And in this case, we see that current I2 and I1, which flows through source of electromotive force E2, resistor R2, and resistor R1, respectively, they are in the same direction as the path we select, so it's counterclockwise. So all of them should be considered as positive in this case, and we can write that epsilon 2 is equal to the sum of I2 times R2 plus I1 times R1. So now we have three equations. Let us write them on a separate slide. So first equation is I1 is equal to I2 plus I3. Second equation, let's check. Epsilon 1 minus epsilon 2. Okay. Epsilon 1 minus epsilon 2 equal to I3 times R3 minus I2 times R2. And one more. It is epsilon 2. Epsilon 2 is equal to I2 times R2 plus I1 times R1. So now we have this system of three equations. We have three unknown. And if, for example, just to make it more familiar to what you did on mathematics, we consider that, for instance, I1 is equal to X, I2 is equal to Y, I3 is equal to Z. So these are unknown parameters, and consider all other parameters, epsilon 1, epsilon 2, and all resistor values as just some numerical values. We get a regular system of three linear equations, and by solving them, you can easily get the right values for unknown parameters, which are electric currents through each of resistors considered in this electrical circuit. So in order to save time and proceed further with the RC circuits, we're not going to solve them, but this is really a very simple system of linear equations, so you definitely can do it yourself. So the most important, the approach, how you get to this system of linear equations. Okay, now we start to consider RC circuits. Okay, so far, as I mentioned earlier, we considered DC current, like direct current, it's called, but usually abbreviation is used, like DC, which was constant in time and constant in the direction of its flow. So if we have electric capacitors in these electric circuits together with power sources like batteries and resistors, then we usually have to deal with electric current, which is still in the same direction, but which changes its magnitude over time. And now we need to understand what is going to happen in such electric circuits and quantify change of electric charge accumulated in capacitor over time, time dependence of electric current, and voltage at the plate of capacitors. So all these parameters should be analyzed quantitatively. Okay, so let us consider a simple electric circuit, which includes a source of electromotive force, resistor R, then we have capacitor C, and here we have such a switch. So which can go between points A and B. So initially, our capacitor is discharged. There's nothing in the capacitor accumulated. And let us assume that we make a contact with point A. So we close this full electric circuit, which consists of electromotive force epsilon, capacitor with a capacitance C, and resistor with some value of resistance R. So now the question will be, how do you think, will we have some current flowing through such a circuit? Do you have any ideas? Keep in mind, you remember the structure of electric capacitor. It's there's two plates with an insulator or vacuum in between them. So there is no contact between these two plates. So what is your prediction? If we contact this point A with the switch, will be some current flowing through resistor R?
The circuit is open, so no current will flow. Probably.
You mean the circuit is open? Why?
Where the A and B does these such as does not connect it, and
okay, yeah. Okay, and now we connect with the switch point.
Okay, then it will flow.
And how?
The capacitor will accumulate charge.
Okay, so that would be the reason why electric current will flow through the resistor R, because capacitor will accumulate charge. Yes.
Maybe, yes.
Okay, yeah, sure, this is correct. And it's necessary to underline that this will happen only for a short period of time, because once electric capacitor is charged, according to the same potential as electromotive force, then electric current will be zero, so it will stop to flow, because once electric charge is accumulated, so and capacitor is fully charged, the circuit technically, even when we connect this point A, remains open because there is no contact between these two plates of the capacitor. They are isolated from each other. It means there is open circuit. But in initial time, there will be some process of charging the plates of this capacitor, accumulating electric charge. And that means that some charge should move through the wires from the electromotive source, should move through the wires and through resistor R to reach this electric saturation of electric charge accumulated on the plates of the capacitor. Once capacitor is fully charged, electric current will not flow because here we will have positive and negative potentials, which will compensate the electromotive force, and electric charging will stop because potentials will be equal, and electric circuit is open. So there is no current, DC current, flowing through this electric circuit. It will be different story for AC current, but that is going to be considered in future. So DC current flows only at the initial moment of turning on while capacitor is charging. Now, once we figure out qualitatively the processes which happen during this charging the capacitor in this particular electrical circuit, let us do some quantitative analysis. So according to the loop rule, second Kirchhoff's rule, we can write for this electric circuit, we have actually one loop here. It's also circuit. We can write that epsilon minus Q divided by C minus I times R will be equal to 0. So this is in the initial moment when we turn on. So we know that the sum of all algebraic sum of all electromotive forces or potential differences, in this case when we have capacitors between the plates of the capacitor, and drop of potential over some resistor, they will for a closed loop of electric circuit should be equal to 0. So based on this equation, so what we can also tell at the initial moment of time, let's say t is equal to 0, that's that moment when we switch, turn the switch and contact point A. Electric current will be equal to epsilon divided by R. So electromotive force divided by resistor. Capacitor doesn't contribute to active resistor, so we don't take this into account. But this is only at t equal 0. However, this current will very rapidly decrease because capacitor C will gain some potential while it's charged. So the maximum charge which will be accumulated at the capacitor at t approaches infinity at some during some long period of time, the maximum charge will be the product of capacitance and electromotive force. We know that the Q, like charge accumulated by capacitor, is the product of capacitance and potential difference between the plates. If we have enough long time to wait, this capacitor will be charged up to potential difference, which is equal to epsilon. And this is the maximum charge which can be accumulated by the capacitor. Okay, now let us go to the, so we define some extreme points, and now let us go to the time dependence of electric charge first and then current. So maybe from this equation first, let us express current. So current will be equal to epsilon divided by R minus Q divided by RC. Now we know that current by definition is the rate of electric charge, which like rate of changing the electric charge. So we can write that I is equal to dq over dt. So it's derivative of changing the electric time. There's some function q as a function of t, which shows how electric charge accumulated at the capacitor will change in time. So derivative of this function over time will give us electric current, which flows through this electric circuit. That's why we can write such a differential equation. dq over dt is equal to epsilon over R minus Q R times C. So let us multiply and divide by C this first term in this equation. So then nothing is changing, but we have the same denominator. And then we can write that this will be equal to minus Q minus epsilon C divided by RC. Okay, now we need to separate these differentials from the left side and solve this separable differential equation. So we can write dq divided by q minus c epsilon, and this is equal to minus dt over R times C. Okay, you see we put Q here for all differential of Q and Q from the same side, and from the right side we have just delta T. Now we need to solve this differential equation, which means we actually integrate it. So the integral of this right integral is quite simple because we have constant parameters R and C. So it will be 1 over RC integral dt, and this will be equal to minus T over RC. Now we need to solve this integral. So in order to do this, we need to have the same expression under differential as in our denominator. So for this, since this is a product of two constants, we can just subtract it from Q under denominator under differential. So that will be dq minus ce, oh sorry, not e, but epsilon, divided by q minus c epsilon. And this will be equal to natural logarithm q minus c epsilon. Okay, so now we have solutions for both integrals from left and right. Now we will equate them and add some constant, because when we integrate, we define the integral within some constant. So we get natural logarithm of q minus c epsilon equal to minus t divided by rc plus some constant, let's call it constant a. So we need to define what is constant a, and this constant a will be defined when we set some boundary conditions. Which boundary conditions we can set? We know that at time t equals 0, there is no charge at the capacitor. As I mentioned, it didn't have any accumulated charge. And we know that Q is equal to 0. So let us substitute T and Q equal to 0. So it will be natural logarithm minus C epsilon equal to A, because T is 0, then we don't have this first term. So we found what is our constant, and since we know the constant, we can substitute it and get the final expression. So it will be natural logarithm q minus c epsilon equal to minus t divided by rc plus natural logarithm minus c epsilon. Now we can put it from the right to the left, put together both logarithms, and taking into account the feature of logarithms, that the difference of logarithms is equal to the ratio, logarithm of the ratio, then we can get this. It will be natural logarithm q minus c epsilon divided by minus c epsilon, and this is equal to minus t over rc. So now, how do we get rid of natural logarithm? We use this exponential function. So we will get the following. It will be q minus c epsilon divided by minus c epsilon is equal to exponent of minus t divided by rc. So now we can express what will be q as a function of time. So this will be c epsilon minus c epsilon times exponent minus t over rc, and this is equal to c epsilon 1 minus exponent minus t over RC. And we know that the product of capacitance and electromotive force, in our case, this is the maximum electric charge which can be accumulated by the capacitor. So it's capital Q, 1 minus exponent minus T RC. And this is the answer. So we see here that if time is equal to 0, so we have 1 minus 1, because exponent in power of 0 will be like e in power of 0, it will be 1. So charge at 0 time is equal to 0. As we set in our boundary conditions. And when t approaches infinity, after a long period of time, or after switching, like turning on the switcher in position to contact point A on our electric circuit, Q at infinity will be equal to capital Q, like maximum charge which can be accumulated, because at t approaches infinity, here we have minus. So this second term will be much smaller than unity. We can neglect with this. So it will be just Q. Okay, so this we have. Let's write it on the next slide. We will need this equation. Will be Q 1 minus exponent minus T over RC. So this is equation which defines time dependence of electric charge accumulated in our capacitor from time, moment of time t equals 0 to certain time t. So now, as we wrote earlier, we know that current is equal to the derivative of this function Q as a function of t over dt. So let us take this derivative and we will get the electric current as a function of time. And this current will flow through the resistor R. This is charge transport, which is required to charge the capacitor. So this dq over dt, and this will be equal. So what do we have here? Let maybe consider still this product C epsilon. It will be better instead of Q. So we will get minus C epsilon exponent minus T over RC. So this is derivative of exponent. And now we need to take the derivative of the argument of this exponent function. This will be times like minus 1 over RC. So now what do we get? We have minus and minus. We have C and C here, we can cancel out. And we end up with epsilon divided by R times exponent minus T over RC. So you see, this is the final equation for the time dependence of electric current, which flows through resistor R and charges capacitor C. And we see here that if time is equal to 0, so exponent is unity, so current is equal to some I naught, like maximum current, and this is equal to epsilon divided by R. If time is approaching infinity, then this exponent is very small, and the current also, because of very small exponent, this current approaches to 0. So now let us, maybe before we consider this graphical representation, you see that in the denominator of the exponent argument, we have this RC product. This is called tau as a time constant of the electric circuit, RC electric circuit, and it represents, its physical meaning is the time interval during which the current in electric circuit decreases by E. E is Euler's number, which is something like 2.718, if I'm not mistaken. So if we consider time equal to tau, which is equal to R times C, then electric current should be equal to, according to this equation which we derive, it will be equal to E in the power of -1 times E naught. And this is in numerical, like it will be 1368 times I naught. So this is the definition of this time constant. And this is very important because this time constant will define how fast electric circuits can, these transient currents can flow in electric circuits. If, for instance, we have constant capacitance and we change resistance, if we increase resistance, it will take longer to charge and discharge this capacitor. If we reduce resistor, so this process will happen much faster. Sorry, and that's why this time constant is a very important parameter. So let us consider graphically how electric charge will change with time. So we know that it goes from 0 and exponentially increases up to some kind of saturation point, which is defined by capacitance and electromotive force. This is maximum charge, which can be accumulated. When we have electric current as a function of time, it will go in opposite. It will drop from maximum value, which is I naught equal to epsilon divided by R, and will go to approach 0 at some time, which is quite long. So also, if we define, like mark here some this characteristic time, which is equal to RC. So this will be I naught times 0.368. It will be by E time smaller than I naught. And here it will be also this characteristic time, tau equal to C, RC, it will be 0.632 times C times epsilon. It will be 0.63, like 63% of the maximum charge which can be accumulated. So our interval, time interval, which is equal to the product of R times C, electric capacitor will accumulate 63% of its maximum charge, which it can accumulate in the this particular electrical circuit. So maybe it would be also useful to define the to carry out this dimensional analysis, just to prove that tau, this product of time and of resistance and capacitance, will indeed give us time and not some other dimension. So dimension of this product is equal as dimension of potential difference divided by current, right, for resistor, and capacitance we can write as charge divided by potential difference. So now potential difference is cancelled out, and we end up with charge in numerator, and here is charge divided by time interval. This is definition of current. So charge and charge cancel out. We end up with the dimension of time interval, and this is unit of dimension of time. So we indeed have the product of resistance and capacitance indeed gives us time. So we didn't have time today to consider the discharge of electric capacitor, so please read it in the textbook. So it's actually even simpler than the derivation of the process of charging electric capacitor, since we don't have epsilon. So if we switch this, turn the switcher to point B in electric circuit, we will just discharge electrically charged capacitor via resistor R. And that is also possible to solve as in the form of differential equation and get time-dependent charge and current, and also potential difference at the electrodes of the capacitor over time. So initially it will be maximum current and maximum charge at t equal to 0, and then current will decrease and charge will decrease to 0 when electric capacitor is totally discharged. So this, please take a look and read in the textbook, and the derivation are actually very similar to what we have already done for the charging process. If you have any questions, you're welcome.
Yes, hello. I have a question. So let's say we have a system of charges, two positively charged particles. And so my question is, how do I express the positions of the particles as a function of time? Since the force it's equal to K times Q1, Q2 over R squared times R hat. But after some time, the position will be different and the force will be different. So like, how do I express the position as a function of time?
So it's, since you mentioned that position, that force changes with the position, so you definitely, if you have a direct approach, you need to write the set of like the differential equation, which will show, like reveal the dependence of force on the position of charges. And because without differential equation, you cannot approach such problems. However, if you have some, let's say, approach which involves the change of potential and kinetic energy of charges, that could be considered a bit differently. However, if there is a direct solution for such a case, you are right that forces will change with the position, and you will need to write the differential equation for such system.
Okay. Do you know maybe how to do it?
Oh, I think that it's like not current topic of the course. So I believe that if you have some particular problem, so you can maybe address this in recitation. So it's like really solving a particular problem.
Okay.
Mm-hmm.
Thank you.
Yeah, here we want to address as much as possible some concepts of physics, since unfortunately in this quarantine time, we don't have an option to evaluate your understanding of the laws and of physics and concepts of physics, like by making some statements and explaining the relationship between different parameters. So it's only solving problems, which is of course very important and definitely shows the understanding of the material. However, still we are lacking of this evaluating of your understanding the physics concepts. So it's really important to focus our time during lectures on deriving, like providing some qualitative explanation of physical processes and deriving these equations, which later are used by you to solve problems. So you have an idea where they are coming from. Okay, and any additional questions?
No, thank you. Goodbye.
Okay, thank you very much for attention, and have a good weekend. Take care. See you on Monday. Bye-bye.
Thank you. Goodbye.